This video explains Optimistic Concurrency Control, also called OCC. It is a transaction processing technique that assumes conflicts between transactions are rare. In other words, it's an approach that optimistically assumes the best-case scenario, where multiple transactions can proceed without interfering with each other. Now, let's explore the key concepts of optimistic concurrency control. The core principle assumes that conflicts between transactions are rare, and transactions can execute without interference. This approach allows transactions to proceed without acquiring locks, which improves throughput and reduces overhead. It's based on the philosophy: optimistically assume the best, but verify before committing. Now, let's understand how it differs from pessimistic concurrency control. Pessimistic control locks resources before use, preventing conflicts but potentially creating bottlenecks. Optimistic control, on the other hand, allows concurrent access, detects conflicts later, and resolves them if needed. The optimistic approach excels in scenarios with read-heavy workloads, where minimal write conflicts are expected. Optimistic concurrency control operates in three distinct phases. Phase 1, the read phase. During this phase, a transaction reads data from the database into a local workspace. All modifications are made to private copies of the data, leaving the original data in the database unchanged. The system tracks the read set, which includes all the data items read by the transaction, for validation later. Phase 2, the validation phase. In this phase, the system checks whether the transaction can commit its changes without violating serializability. It verifies that no other transaction has modified the data since it was read by the current transaction. This is typically done using timestamps or version numbers to detect conflicts. If validation fails, the transaction must abort and restart. Phase 3, the write phase. If the validation succeeds, the changes made by the transaction are permanently applied to the database. The local modifications are written to the actual database. The transaction commits and releases all resources, making the modifications visible to other transactions. Let us now explore the validation techniques used in optimistic concurrency control. One common technique is timestamp-based validation. Each transaction is assigned timestamps at different stages. Start of transaction at time t when transaction t begins, validation of t when t enters the validation phase, and finish of t when t completes after the write phase. For two transactions t sub I and t sub j where I is less than j indicating that t sub I started before t sub j, the backward validation rule is as follows. If finish of t sub I is less than start of t sub j, then no conflict is possible and allow commit is true. Else if read set of t sub I intersection write set of t sub j is an empty set, which means there is no overlap between t sub i's reads and t sub j's writes, then allow commit is true. Else conflict is detected and abort and restart. Another technique is version-based validation. Each data item maintains version information. Every data object has a version number or timestamp. This version is increment when the object is modified. The transaction records version numbers of all objects it reads. During validation, for each item in the transaction read set, the current version is equal to database.get version of the item. Read version is equal to transaction.get read version of the item. If the current version is not equal to the read version, indicating that the data has been modified since read, then return abort and restart. If all versions match, it is safe to commit, so proceed to the write phase. Let's walk through an example scenario to illustrate how optimistic concurrency control handles conflicts. Consider two transactions, T1 and T2, attempting to modify the same account balance concurrently. Transaction T1 starts at timestamp 100, reads account A with a balance of $1,000, calculates a new balance by adding $200, enters the validation phase at timestamp 130, and then updates account A to $1,200 during the write phase. Simultaneously, transaction T2 starts at timestamp 110, reads account A with a balance of $1,000, calculates a new balance by subtracting $500, enters the validation phase at timestamp 140, but the validation fails because a counter was already modified by T1. The result is that T1 commits successfully with a balance of $1,200, while T2 must abort and restart due to the conflict detection. Now let's examine some implementation examples of optimistic concurrency control through pseudocode. First, here's a basic OCC transaction. The function execute transaction takes a transaction as input. In phase 1, the read phase, a local workspace is initialized along with empty read set and write set. For each operation in the transaction, if the operation type is read, the item is read from the database, it is stored in the local workspace and added to the read set with its object and version. If the operation type is write, the item is stored in the local workspace and added to the write set. In phase 2, the validation phase, the validate function is called passing the read set, and if it does not validate, then the transaction is aborted. In phase 3, the write phase, for each object in the write set, the database write function is called to update the object in the database, and the database increment version function is called to increment the version number. Finally, the function returns commit. This simplified pseudocode demonstrates the 3 phases of OCC. In real implementations, additional mechanisms for conflict resolution and deadlock prevention would be included. Next, let us look at a validation function implementation. The function validate takes read set as input. A global lock is acquired during validation using the acquire validation lock function. For each entry in the read set, the current version is equal to the database get version for the objects. If the current version is not equal to the entry version, indicating that the data has been modified by another transaction, then it returns false. If the loop completes, meaning validation is successful, then it returns true. Finally, the validation lock is released using the release validation lock function. A separate function handle conflict takes a transaction as input. Strategies for conflict resolution can be a simple abort and restart, back off with random delay, or priority-based resolution. A delay is calculated using the calculate back off function. The sleep function is called passing the delay. Finally, the transaction is executed using the execute transaction function, passing the transaction. The validation phase is critical for ensuring serializability. Note that a short-term lock is used during validation to ensure atomicity of the validation process itself. Now, let's weigh the advantages and disadvantages of optimistic concurrency control. Some advantages are as follows. There is no locking overhead during transaction execution, reducing contention and improving concurrency. It is deadlock-free by design since no locks are held during transaction execution. It is excellent for read-heavy workloads where conflicts are rare and most transactions can commit without interference. It provides improved throughput in environments with low data contention. It works well in distributed systems where locking across nodes is expensive. It provides simpler implementation compared to complex lock management protocols. Some disadvantages are as follows. There is wasted work when transactions abort and must be restarted after validation failures. It provides poor performance under high contention due to frequent transaction aborts and restarts. There is a starvation risk for long-running transactions that repeatedly conflict with shorter ones. Validation overhead can become significant as the number of concurrent transactions increases. There is memory overhead for maintaining private workspace copies of data for each transaction. There is need of complex conflict resolution strategies needed to prevent repeated aborts. Let's explore some real-world applications of optimistic concurrency control. Many modern database management systems or DBMS implement OCC, including PostgreSQL, which uses multi-version concurrency control, also called MVCC, a form of OCC. Microsoft SQL Server offers optimistic concurrency through row versioning. In-memory databases like Redis use OCC for high throughput. OCC is valuable in distributed environments where cloud databases like Amazon DynamoDB use OCC for scalability. Microservices use optimistic locking for data consistency, and blockchain systems employ OCC like validation for transactions. Web applications benefit from OCC in scenarios like collaborative editing tools, for example, Google Docs and Office 365, e-commerce platforms for inventory management, and form submissions with version tokens to prevent duplicate processing. OCC enables better user experience in offline-capable apps that sync when connectivity returns, mobile applications with local data caching, and progressive web apps, also called PWA, with conflict resolution. OCC is particularly effective in environments with high read-to-write ratios and low contention. Many systems implement hybrid approaches, combining optimistic and pessimistic techniques based on workload characteristics and conflict probability. In summary, let us review the key takeaways about optimistic concurrency control. OCC operates on the assumption that conflicts are rare, allowing transactions to proceed without locks. The three phases read, validate, write form the foundation of the OCC protocol. OCC excels in read-heavy workloads with minimal contention between transactions. Validation techniques using timestamps or version numbers are critical for detecting conflicts. Regarding future trends and research directions, there can be hybrid concurrency control combining optimistic and pessimistic approaches, adaptively based on workload characteristics and conflict patterns. Machine learning integration can be used to predict conflict likelihood and dynamically choose optimal concurrency control strategies. Enhanced protocols can be created for distributed OCC in geo-distributed systems with partial connectivity and varying latency. In conclusion, optimistic concurrency control represents a powerful paradigm that balances performance and correctness by trusting that most transactions can complete without conflict, while still providing mechanisms to ensure consistency when conflicts do occur. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.